Hello everyone. Welcome to TS session for week 4. So basically in this session, I'll just share the slide first. Hmm, okay, let me share. First, I'll be talking about classical Hall effect. And one second. Yeah. So first, I'll talk about the classical Hall effect. Then I'll discuss the Landau quantization, which is the single electron motion of single electron under the application of magnetic field. Then I'll move to integer quantum Hall effect. Then a little bit some discussion on fractional quantum Hall effect, and later I'll end up the session with discussion something related to composite fermions. So basically, whatever questions were given uh, in the assignment 4, so I am gonna discuss some similar concepts, so which will help you to solve some of the assignment questions. So as per the instruction, as you know, I cannot directly answer or rather discuss the assignment questions and directly. So for that's why I have made some sample questions and some similar like through some similar concept clearing I'll be trying, so approaching those questions so that you can through the understanding of whatever I'm going to discuss, uh, that will that is for sure gonna help you to solve the rest of the assignment questions whatever is given for this week. Okay, so first so you need to understand what is classical Hall effect. Okay, first before quantum Hall effect. So first we'll look what is this vector. This is standard like geometry. So this is the standard geometry, as you know, for the classical Hall effect to understand the phenomena, right? Which was this which was discovered by Hall. So this is basically a metallic three-dimensional sheet, right? This one, it's a metallic sheet. Rather, I'll just decrease the width. It's metallic sheet. Okay. So it has some certain length, width, and thickness. So as you can see, we have applied a voltage along the x direction. So basically, we're applying some voltage along this direction. So current is flowing from this end to this end. So you can consider ki it's basically a closed loop, right? So along this direction, current is flowing basically. So here the axis representation. So current is flowing along the x direction. At the same time, but applying the magnetic field along the z direction, right? So that's why I mean we are applying the magnetic field along the z direction. So because of the Lorentz force, so electrons are basically will start moving, right? Charged particles are moving under the influence of this applied magnetic field. So our applied voltage, so along the x-axis. So in the presence of the magnetic field, so there is a full magnetic. That's the force is called the Lorentz force on the moving charged particles. So that's just like Lorentz force is, as you all know, that's the charge uh, times v cross speed. So the direction of the force basically it is will depend on the uh, cross product of the velocity and the applied magnetic field. That is why the charge accumulation is happening, and there is a need after a certain time in the equilibrium. We get the we get a voltage that has been built up along the y direction, right? So this two also. Hmm. So this is called the Hall voltage, and after a certain time, so there is a steady state when this force and this force basically become equal in the magnitude but opposite in direction. So there is no more further charge accumulation. So this voltage is, yeah, this effect is known as Hall effect. and we can measure the Hall coefficient, which is nothing but the ratio of the applied electric field, mm, sorry, the Hall field, and in the y direction. So this put to develop, I mean, along the y axis, right? Y direction. This is whole field to our voltage. That is, I mean, this field divided by current, which is along the x axis. So that is Zx, and the applied magnetic field. This is called Hall coefficient. Okay, you can easily calculate this. So if you just put all this thing together, you will see this thing is happening. I mean, if you take care of all the, like, if there's a negatively charged particle present in the system, this Hall coefficient become negative, right? So I'd like to discuss here that if we look at, so this is Hall coefficient, right? This one. For the negatively charged particles for the metal. I'll move to next slide. So this is what I was talking about, the rho xx, which is longitudinal resistivity, and rho xy, which is the transverse resistivity. It's, so transverse because their resistivity is along, we're missing along like y-axis, which is perpendicular to the x direction of the current, and this is the resistivity of the material we are measuring along the direction of the current. Okay, so sometimes it's also known as the magneto resistance, but this is not very common. So because this magneto resistance term we are using for the materials in which the resistance is field dependent, is the magnetic field dependent, but in this case, in general, all materials do not show the magneto resistance effect. So in general, this actually independent of the magnetic field. This is the resistivity. Okay, so we can see from here the resistivity is nothing but 1 upon like where you mu is the mobility. So this is the resistivity, right? General expression 1 over n e mu, where n is the charge density and mu is the mobility and n is the Coulombic charge electron. So this is independent of magnetic field. This is independent of the B. So this is almost fixed. Is of course the pressure dependent, but here we are looking for looking the field dependence of resistivity. So this is the transverse one, which you can see, which is proportional to B, right? So if you look at the resistance and the resistivity released, so they are related. That our resistance is basically rho times L over A, right? If you look at the dimension of the resistance, so this is rho, dimension of rho multiplied by L, and 2 minus like this is the standard thing. We have already done this thing, right? So this is ohm. So dimension of this is the dimension. Okay. For 3D, what is happening? For 3D, actually, mm, for 3D actually d equals to 3, right? So this will become R rho by L, right? So resistivity is actually same for two-dimension systems. So why I'm discussing here, there is for two dimension that you will understand in the next slide. Okay, so that is why it's important to understand this, I mean, for different dimensions. So one more thing about the transverse resistivity. So as I had discussed in the first slide, that the transverse resistivity is actually nothing but the Hall coefficient, right, multiplied by the magnetic field. So what was the Hall coefficient? That was the 1 over E. So now it's like Hall coefficient multiplied by B is called your transverse resistivity. Please remember all this formula. This is very important to solve some questions. Yes. So on this 2. Okay. Basically, the transverse resistivity or whole resistance, which you can also say that all resistivity resistance. So this is actually like proportional to B, because here this coming over here, so that means with increasing magnetic field, your Hall resistivity will also increase. So it's linearly changing with the magnetic field, right? That is proportional to B, but it's linear with slope 1. And the longitudinal resistance, as you can see, this has no dependence with the magnetic field. So this is constant. So for a system of three-dimensional presence of magnetic field, this will show you how the resistivity, like both the transverse and the longitudinal, will change. Will I mean how it behaves with the change with respect to the magnetic field. This is all about the classical Hall effect. So now let's go to the quantum Hall effect, quantum domain, and we'll see how it's different from the classical Hall effect. Okay, give me one couple of minutes. I'll just come. Just I need to add something here. One second. अरे क्या फोक्सी चल रहा है So, starting with the, so this is, you have already seen, right? This is for the classical Hall effect, and this is how the transverse and the longitudinal resistance are. So the transverse part is basically dependent on the magnetic field, and this is not, doesn't depend on the magnetic field. And this is the your Hall resistance basically. So that I have already discussed. This is Hall resistance. This part has been discussed in the first slide. And this is how the transverse and the longitudinal resistance will depend on the applied magnetic field, right? These two curves basically indicate that. So, so if I measure like, so okay, so this has been the Drude model of what I would expect to see if I measure the Hall resistance. Like if I measure the longitudinal resistance, it's a function of magnetic field, and the simplest, as you can see here, there is no magnetic field dependence on the longitudinal resistance, and we have a linear dependence with the magnetic field for the Hall resistance. So that's the Drude model, and now what I'm going to do is one second. So now what I'm going to do is I'm going to turn this sample into a bunch of Swiss cheese. I'm gonna cut holes in it. So you can see this holes I have made. So I'll mark with red so that it will So it will be easy to understand. So this you can see, right? This you can see, these holes. Okay, I'm gonna cut holes in it. When I cut holes in the samples, an interesting thing happens. So this regions that do not conduct at all, right? Of course, there is this completely empty. It doesn't I mean, if I so simply try to understand in such a way, if I simply cut these things, I mean, if we remove some of the portions from the conductor, so this will not contain. This is completely isolated. So this will completely isolate it, and this doesn't contain any states, physical state, so that electron can be accommodated in those states. So that's why the conductivity, those region will not conduct, right? So this portion will not conduct at all, right? Will cause the current flowing through the sample to be squeezed. So the current goes through an effective narrower width, which means that my longitudinal resistance will go up because this W goes down. So once again, I see geometrical effects in my longitudinal resistance, but notice that the whole resistance has not changed at all. Even this is the very important part. So the thing is, like if we go back to our earlier equation, so previous slide, so how this transverse resistance will depend, or on the width. So this is the our longitudinal resistance, right? Or the this is rho L by A. So keep in mind this formula, because this is going to answer this questions. So current is flowing through the sample to be squeezed. So the current goes through an effective narrower width, which means that my longitudinal resistance will go up, right? Because exactly, because this W actually goes down. This W you can see, right? So it's like if I simply do. This is resistivity, and the length of the conductor divided by this is the width times, sorry, this is the width times maybe let's say thickness. So what happens? W is going down, right? As this portion, this channel is getting narrower because of the existing holes. So it's inverse. So the resistance is inversely proportional to W. So as the W goes down, so R will go up. This is as simple as that. Okay. So that is what this is. Keep in mind, this is your RXX. There's a slight difference. This is RXX and RXY. This is longitudinal. Okay. This is longitudinal resistance. And I see the geometrical effects here, right? In my longitudinal effects. But notice one thing. Notice that the whole the Hall resistance, which is basically RXY, right, has not changed. This is this is what we have already got for when we didn't have any holes present in the system. In that condition, whatever we had, we're getting the same thing in the Hall resistance part. So it's exactly so it not changed at all through like though I drastically modified the geometry of the sample by cutting holes. So it's okay. So and the reason for that is that as the like current goes around this holes goes between these holes, the current will have to speed up a little bit, and speeding up that will increase the Hall resistance. When I integrate the basically see, so see the current goes around these holes, right? That has to. So this holes goes between this holes. The current will have to speed up a little bit, and by speeding up that will increase the Hall resistance, right? When I integrate the transverse electric field, I get the same value independent of the sample geometry. Okay, so I want you to remember this Swiss cheese model. If I have a conductor and I punch holes in it, it will still get the same Hall resistance as that the conductor without the holes. So this Rxy, the Hall resistance, measures the density of this extended regions. You can see here's my density. There's the extended region that do conduct current. I'll move to the next slide. Current. Okay. So the rule number zero, like here's what happens if I have a high mobility samples. You can see that we start to deviate from the Drude model in both B Hall, and the longitudinal resistance uh, starts to develop plateaus. The longitudinal resistance drops down and start to show this drastic oscillation which go all the way to zero. And then this is the signature of what is called the quantized Hall effect, because the Hall resistance seems to like favor the certain magical values, where for an entire range of magnetic field it stays at a single Hall resistance value, hence the name quantized Hall effect. And on the same notebook where Professor Klaus on Singh when he first observed this feature. One second. Observe this feature, he immediately deduced this formula, and there's that one's page of his like logbook, where that's the page that won him a Nobel Prize. Is a recognition that the steps here are in units of h over e square divided by an integer, right? So that's the all we need to know about the classical Hall effect. Now if I was like were to study anything quantum, I'm going to I can have to acknowledge the fact that electrons are not classical little marbles particles running around. They actually have a wave nature, right? And so they can interfere with each other. In particular, the presence of the magnetic field whenever cyclotron motion will be only discrete angular momenta, which will allow the phase to change, the complex phase to come back and constructively interfere with itself. Okay, therefore, there will be only discrete allowed energy levels, values. That's the Landau quantization. Okay. So this is like beginners of quantum mechanics. The Hamiltonian of a free particle is like the the free particle is the kinetic momentum, like this squared by twice m star. There is a potential v is zero for the free particle, as you know. So now in the presence of magnetic field, so what the momenta is, it's really, is it the rate? One second. Magnet. So what momenta really is? It's the rate at which the phase changes per unit length. Okay, that's the momenta really is. Now there's actually two things that can cause momentum. One of which is the fact that particle is moving. The other of which is if the particle is in a vector potential. So if we know what the in the order to know what's the kinetic momentum in its presence of magnetic field, we have to take the canonical momentum and subtract out the part of that momentum which is just due to the vector potential. What remains is identically the kinetic momentum, and of course kinetic energy is pieces pi squared v squared over twice m. So we have to choose. We then introduce our magnetic field in its manner. Let's choose the so-called Landau gauge, where our vector. So this is the Landau gauge. Okay, this is. I mean, it's just a choice to simplify the problem. So I can mention here it's Landau gauge. 1 second. Um, okay, this is the Landau gauge, where our vector potential is of this form. The curl of this vector potential, right, is my magnetic field. This is what it looks like. Then the Hamiltonian, which has like three components, you can see. So this is my Hamiltonian, ultimate Hamiltonian. I'll change this. Okay, fine. This is the kinetic part. This is second part. So this is how it looks. Then this so this is the canonical momentum, right? So this is how it looks like. Then this Hamiltonian, which has all three components of my canonical momentum, it's going to have a pi square and a pi square. But now the pi square component I have to subtract away zero. I don't have any contribution there, but pi square component I have, because that way I have chosen the gauge, right? So pi square component I have to subtract away this vector potential, and here I have just reversed the order of this two, because the square, just by inverting the ordinance squaring, it's okay. So one of this wave function going to look like, the wave function is uh, it's the Heisenberg, I'm sorry, the Schrodinger equation, right? I've got a Hamiltonian at the eigenstates. If I examine my, I get my Hamiltonian carefully, I can see that my entire Hamiltonian commutes with the y momentum, right? So which means that if we want to express this wave function in terms of product of the product of a x dependent wave function and y dependent wave function. So this is actually e to the k. Sorry about that. I can like separate that as a product, and I have got the momentum eigenstate to the so then if this is the form of my wave function, my Hamiltonian, this momentum supply moment operator, just pull down the exponent, this exponent, and so factoring out this b square out of the term gives me the following prefactor, and I get an expression with I have my momentum in the x direction, and then I have some prefactors times the x operator minus a constant square, and this are my this is how my Hamiltonian for this x component, right, of the wave function. The solution to that is Hermite polynomials, and you can see that they're like this one. You see that here, what if this is this term here is just the displacement term. I'm going to call my orbit center coordinate. This is harmonic oscillator, and x minus this value where my local minimum of the harmonic oscillator is. And so I'm going to call this coordinate x sub k orbit center coordinate for my harmonic oscillator. So this is what my potential look like. This one, this is the potential profile, right? The potential profile, and its momentum is in the x direction. Okay. And parabolic potential centered. So it's called orbit center coordinate, which is actually a function of my momentum ky. So the larger my magnetic field is, the more curvature I have in my parabolic potential. And we know that the quantized solution, the solutions to the harmonic oscillators are equally spaced levels with h bar omega c, right? That is mentioned here. So oscillate in this case the frequency, like the cyclotron frequency, and this is by definition the Landau levels, right?
And this is the land of quantization, and I've sketched by hand the lowest. One second. The lowest land of level first, second, and third, all separated by h cut omega c, and the the momentum of the electron in these orbits. The momentum is going into the page on the right and out of the page to the left. So you can imagine if I were to consider that what is this orbit really doing. The electron flux is coming out of the page here and then going into the page here, and that's the cyclotron orbit, right? So those wave functions, if you are not comfortable with quantum mechanics, then just keep the idea that there are some states which are separated in energy by h cut h bar by omega c. So we have zoom in the splitting, so each one of this in the presence of magnetic fields, how it will split. So under the application of magnetic field, so how it will. So for if we don't apply any magnetic field, so like So if I zoom this portion, you can see here under the application of magnetic field. So it's because of the spin splitting. Okay, so each one of this in the presence of magnetic field will split into a spin up and a spin down and in a spin down level. Okay, so we arrive at a harmonic oscillator solution. Energy is separated by integers of the multiples of the cyclotron frequency. The exact wave function is done for polynomials which are centered at the orbits and the coordinate which is itself proportional to the momentum in the y direction, right? So we can figure out how many of these states exist inside of a two-dimensional sample. Okay, so recall this wave function here, this one, and it represents it has an electron to the q and dependency into the point into the page, so you can imagine this wave function extending all the way out with some mm, the board, right? So how many of this so this it's the y direction in the board, the states do I have? Let's say that I have samples that's L unit, it's deep, okay, into the board in, in this direction. Basically you need to visualize actually how's where is the next nearest orbit center coordinate whose wave functions are going to be orthogonal to this one. So given that I have a wave function whose which has a momentum plane wave behavior into the page, given my sample is at a distance L, the two momenta in picked with just assuming periodic boundary conditions, the two nearest momenta that will be orthogonal to each other will differ by the two pairs over L, right? So okay, this is an integral symbol. This one, this is it's kind of 0 to L. Okay, I don't know why it's like yeah, it's integral symbol. This two states will be orthogonal if the angle over the length of the sample of the two different momenta differ by pi's over L, two pi's over L. Okay, so that is you know this is the momentum difference q minus k equals to 2 pi by L. So if this is the orbit center, this one, if you consider, okay, of this is an orbit, you can imagine the other orbit at x of q will be centered like xq, x, and this is the xq, where it will be centered, okay, at this position, and we can, if the momenta changes by 2 pi over L, then we can determine the orbit center coordinate associated with that shift, and that's just 2 pi over L times the magnetic length. I can then calculate how much flux through this area, uh, the magnetic flux. Well, I know the geometry of this. It has a length of 2 pi over L for the strip, and it has a depth over L on the board. That's the area, right? And when I multiply that by the magnetic flux density, and I get that I have one flux quantum. So for a given each, like given state, the next nearest orthogonal state will have which is as what is associated with an area of one flux quantum. Okay. And I have to move to the right as soon as I have integrated out the area of one flux quantum between this orbit path and the next orbit center coordinate. Then I have my next data, I have next orthogonal state, etc. So you can see that this flux quantum. So now I'll move to the next slide. So here you can understand better. So you can see that this flux quantum, each of the states basically. So you can see that this flux quanta, each of the states basically is going to be separated by one flux quantum, right? So if I know how many flux quantum I have in my sample, I know how many orthogonal electron states I have in my sample, right? So very good. Uh, Now I'm going to talk a little bit about the electrons. A magnetic field we are gonna take. We are going to draw as a cartoon. So for that I'll move to the next slide. Yeah, focus here. Yeah. Please try to remember all the formulas that I'm highlighting, because that will help you to solve the questions, assignment questions. I mean, at least you will get the idea. So these are very important, although. Okay. So look at here. Hold each electron orbit with its own flux quantum. So here you can imagine, so this is an electron traveling in a cyclotron orbit constructively, and this is the lowest Landau level. Say for my cartoon, this is the lowest Landau level, represents a flux at least one. Okay, focus at one. And this is my cartoon, so that represent a flux quantum. Okay, so there is a certain area, as you saw in the previous slide, there is a certain area associated with the magnetic flux quantum. So if I have a certain flux quantum density, so this is here, I have 16 flux quantum. Okay, total 16, just for the visualization purpose. 16. Okay, 16 flux quantum per unit for this unit area that's associated with the magnetic field. So you can see uh, my magnetic field times the area of the single flux quantum is the this one. Okay, so this is the flux quantum. So if I want to know how many flux quanta, I take the flux density and divide it by flux quantum. Okay, this is the filling factor. This is how we get to know, and that tells me the number density allowed electrons state. I can define a filling factor for this, right? It's a unitless density. So imagine that I have one electron per flux quantum. So if right now it's a filling factor of 0, okay. My unitless density is 0 electrons. So 1 electron per flux quantum. So right now I don't have any electrons. So say my filling factor is 0. My unitless density is 0 electrons. If I were to have 1 electron for 2 flux quantum once again, then I have to move here. I mean, that's for 2 quantum unit. Then the mu will become half, right? That is my cartoon for a single electron traveling in a cyclotron orbit, when half of this flux quantum will not have an electron orbit around them, and half of them would, and so this would be filling factor 1, half 1 electron per 2 flux quantum. This would be filling factor 1. Then move to the next situation. This This will be the situation when you have a filling factor of 1, which would mean that every single state and the lowest Landau level spin down is occupied now or spin up. So this is my angular momentum index I equals to 0. So if I want to add any more electrons to this, all of these states are occupied, I would have to add a spin down electron, and that spin down electron is going to be separated by the same on energy, right? These are the details for this. So if I want to add more electrons, then I can add, right? And higher angular momentum spin up, or even hiring the same higher angular momentum spin down. And so that's going to be my Landau levels for spectrum. So if I have a filling factor of 3 halves, so look at this condition, this 3 halves. Okay, it means that around, on average, those 3 electrons for every 2 flux quanta. So the lowest Landau level is filled for every electron, and the next highest level is half occupied. Then here's the filling factor, mu equals to 5 by 2. Okay, the next, I'll move to the next line. 1 second. It's not, this is for 5 by 2. Okay, this one. So this is for 1. And let's consider the fact that is we are never going to have a sample that just extend to infinity. We have to acknowledge that fact that this samples will terminate. I will cut a centimeter by centimeter square piece, or half a millimeter is half a centimeter by half a centimeter, and I'm going to have some sort of boundary. What is going to look like if I have a boundary? Imagine that electrons cannot cross this line. So for that, yeah, this one. So this is my boundary. Okay. So electron cannot cross the line. Then what will happen is the electrons will, when they try to execute a complete orbit, they will instead be scattered specularly off of this wall, and they will shoot along. You can see that, whereas inside the bulk of the sample, when the electron orbit does not intersect with any edge potential, the electron orbit is stationary. But here at the edge, the so-called edge state, what happened? Sorry, something is. Yeah, it came. Yeah. So this eight states. These are called eight states, right? That are and the motion that's there is a net motion of the electron. It does not stay around a single flux quantum. It slides along the edge, and this chiral motion is the characteristics of each state. Okay, so here's my diagram for the eighth state. Next, move to the yeah. So this is very important. So this is a plot of all the allowed states. Okay, here the bulk of the samples here, the lowest Landau levels, spin down, spin up, spin down. So you can see they are all separated energetically, and as I indicated before, as I get close the sample, let me show you what happens here. So yeah, so in the bulk of the sample, if it have a certain angular velocity, right? So which is the rotating around its flux quantum, then it's going to complete its orbit in a period of time, right? If I have a wall, right, right down the middle of the my flux quantum, it will only in a time period of so it will leave the wall and then hit the wall again, and then it will repeat that motion. It will leave the wall and hit the wall, leave the wall. So it's like kind of a process. So it's smaller time than the tau, and since the energy is inversely proportional to the frequency, it means the states the age the states the age have the higher energy than the states in the bulk. You can also think of it as a quantum confinement, right?
So this age have higher frequency energy, right, than the states in the bulk. You can also think of as a quantum confinement. You can think as the age state is squeezing off against the wall, and so I'm going to draw the spectrum of the lowest level state, right? I'm going to draw the energy in my energy versus position, energy versus position. The energy is nothing going to slide upward. X naught is the position of my hard wall, and you can see how each of the states as they get close to the wall will increase in energy, right? So here see, I'm going to apply a so-called filling energy. This is my Fermi energy level, right? This one. This is the Fermi energy, and as we know from the Sommerfeld theory of metals, if I want to study the conductivity of a metal, I should identify what its Fermi surface looks like, and I should only need to consider the behavior of electrons near the Fermi surface. So if I set a Fermi energy, I I only need to worry about that what electrons are doing right at the Fermi energy. So let's make a plot of this thing that's kind of strange about the Fermi surface of this land, and I'll quantize system, and it is that there's an actual coordinate in real space where the Fermi surface lives. Let's draw a little diagram. So for that, I'll move to the next slide. So this one, it's very important to understand. Yeah. So draw a little diagram. There, here I could that you can see. So here I could imagine this two age states are coming out of the board here. My world, here's the two age state. If I draw my Fermi surface, I can draw it. My Fermi energy happens to be halfway between the two Landau levels. My family surface is physically located at the Fermi surface is physically located at a coordinate on the age, and I only once again because it's a metal. As long as my temperature is small compared to this energy range, I only need to understand the kinetics of electron near the Fermi surface, and then I will understand what the conductivity will look like. That's our goal. Our goal is to understand how I measure those longitudinal and transfer distances where this plateau is coming from. So now we know we need to only consider what's happening here in order to be able to understand the quantization of Hall resistance. Uh, okay, so there's my Fermi surface, and it's my eighth state diagram now. The Hall resistance.
we know. I would like to do the calculate what is the Hall resistance associated with the Fermi energy exactly in one of these gaps, right? So here I have got a filling factor of 2 because of the two levels are completely filled in the bulk. The Hall resistance is be over any that's the classical value, and but because I have exactly two filling it means the density of electrons is exactly twice the density of flux quanta, but the flux point of density proportional to the magnetic field, right? That you can see here from this equations. So that means that the electron density is proportional to the magnetic field, which means that I have something proportional the magnetic field in the denominator and something proportional in the magnetic field in the numerator. When I take that ratio, they cancel and I get universal value, right? So this tells us one important result. The, the Hall resistance of a completely filled Landau level is 1 over like integer times the resistance quantum h over e squared, right? And so this is what it looks like, and when we have got our this, it's look like in the transport measurement, and this is the transport measurement data that you can have a look once. So you might think we are done well. No, we are not. Why are we are not done? Because even though when the Fermi energy is in the gap, but my Hall resistance is 1 over n times the resistance quantum. The problem is, as I'm going to show you, Fermi energy is never in it gap. It's never in a gap. What to do? I mean, where like when I say we have got a huge degeneracy of state, number of states at the age is trivially small. There's a huge degeneracy here. What really happens is if I add one, if I've got a few electrons here, then I can remove electrons, and as soon as I remove the last electron from this Fermi energy will from this the Fermi energy will jump immediately. Okay, so we'll jump immediately right, and right down to here. So we can't even get we would be able to measure this as a whole Hall resistance, but it would be instantaneous, and so would never really see a long plateaus. There is no range of magnetic fields. Well, I'm going to see this quantized resistance value, so we are still missing one detail, and the best thing I believe was uh, Pauli's. Who betrayed the solid state physics. Yes, I figured the quote's brilliant. So, yeah, 1 second. So it will be like modified when the disorder will play another load. So that is a different context also. So, like, we have a lot of things to discuss that I can continue, and in my next lecture, I think it's already almost. You can ask me if you have any other doubts or questions, whatever. So you can also go through the remaining slides that's on the fractional quantum Hall effect, or else I'll continue with this in my next TS session in the week 5. I'll try to cover the remaining topics.
So these are very important. Just go through the all the slides and this video that I've recorded today. So if some of us are not uh, present here, so you can just have a look, and I hope this session will help you to solve some of the questions which were given in the assignments. So okay, with this I would like to end today's session, and one second.